Hey everyone, and welcome. You know that little lock icon in your browser? Or when you send a secure email? Well, every single time you do that, you're relying on this incredibly clever system that, honestly, most people have never even heard of. Today, we are going to pull back the curtain on hybrid cryptography. It's the real unsung hero that makes our entire secure digital world even possible. All right, let's get into it.
So why are we even talking about this? Well, this whole thing started with a fantastic question I saw from a developer online. They were wondering why their company was using two different kinds of encryption. They asked, isn't one really strong method enough? Is this just an unnecessary extra layer? And that is the perfect question, because it gets right to the heart of a huge fundamental challenge in digital security.
To answer that, we really need to understand the two main characters in our story, symmetric and asymmetric encryption. The best way to think about them is like two specialists, right? Each one has a unique superpower, but also a critical weakness.
Okay, first up, we've got symmetric encryption. The idea here is actually super simple. You have one single key to lock the data, and you use that exact same key to unlock it. It's kind of like a secret handshake. Both you and your friend have to know the same secret handshake beforehand to prove you're in the club. It's simple, it's direct, and when it works, it's really effective.
Now, the superpower of symmetric encryption, it is unbelievably fast. I mean, blazing fast. Algorithms like AES can encrypt huge amounts of data. We're talking streaming a movie, encrypting your entire hard drive in a blink. But, and this is a big but, it has a fatal flaw. How do you and your friend agree on that secret handshake if you're on opposite sides of the world, talking over the open, insecure internet? If anyone is listening in when you share the secret, your entire security is completely broken. That's the key distribution problem.
So to solve that exact problem, how to securely share the secret, we need to bring in our second character. This one is designed for precisely that job.
And that is asymmetric, or what's often called public key encryption. Instead of one shared key, you get a pair of keys that are mathematically linked together. The perfect analogy here is a personal mailbox with a slot. You can give your address and the location of your mail slot, that's your public key, to absolutely everyone. Anyone can drop a message in, but only you, with your special private key, can actually open the mailbox and read what's inside.
And this is how it brilliantly solves that key distribution problem. You can shout your public key from the rooftops, and people can use it to send you secure messages that only you can ever read. It's a genius solution. But you guessed it, it has its own fatal flaw. The super complex math that makes it so secure also makes it incredibly slow and power-hungry. If you tried to encrypt a whole movie with this method, well, you'd be waiting for a very, very long time.
And just how slow are we talking about here? Well, depending on what you're doing, asymmetric encryption can be anywhere from 100 to 1,000 times slower than a symmetric method like AES. That's not a small gap. That is the difference between an app that feels seamless and one that's totally unusable.
So here's the fundamental trade-off we're stuck with. On one hand, you've got a method that's super fast, but can't share keys safely. On the other, you've got a method that shares keys perfectly, but is way too slow for the big jobs. The thing is, we need both. We need speed and secure key exchange. We can't just pick one, so what on earth do we do?
Well, we get clever. Instead of choosing one over the other, we build a system that uses each of our specialists for the one thing it does best. And this, my friends, is hybrid encryption. It's the elegant solution that powers pretty much the entire modern internet.
If you remember one thing from this whole explainer, make it this analogy. Imagine your diary is the large message you want to protect. The small, simple key that locks the diary, that's your fast, symmetric key. And the big, heavy, complex safe, that's your slow but super secure, asymmetric encryption. See what's happening? You use the fast lock for the big diary, and then you use the secure safe to protect the tiny little key.
So how does this actually play out in the real world? Let's walk through it. First, your computer generates a brand new, totally random symmetric key, just for this one time, this one session. Next, it uses that fast key to encrypt all your actual data, the email, the website, whatever. Then, here comes the magic trick. It takes that small, symmetric key, and it encrypts that key using the recipient's public key. That's our secure mailbox step. Finally, it just bundles the big encrypted message and the small encrypted key together and sends them both off. The person on the other end just reverses the process. They use their private key to open the safe and get the symmetric key. And then they use that key to unlock the data. Boom. Speed and security working together in perfect harmony.
Now, in the professional world, the asymmetric part of this whole dance, the part that protects the session key,
has a name. It's called a Key Encapsulation Mechanism, or a KEM. This is literally the safe from our analogy. Its one and only job is to securely wrap up that little symmetric key.
And the symmetric part, the fast workhorse that encrypts the actual bulk data, that's called the Data Encapsulation Mechanism, or DEM. That's the simple lock on the diary. By splitting the job up like this, we really do get the best of both worlds.
Now, this isn't just some cool theory from a textbook. This exact KEM and DM model is running silently in the background of almost everything you do online every single day.
Just take a look. That little lock icon in your browser, that's TLS, Transport Layer Security. And it is a classic hybrid system. It uses an asymmetric handshake to securely agree on a symmetric session key. And then it encrypts all the website traffic with that fast key. The very same principle is used for secure email with PGP, for secure file transfers with SSH, and even for how cloud providers protect your data using something called envelope encryption. It is literally everywhere.
But of course, the story doesn't end there. Technology never ever stands still. And the next huge challenge is already on the horizon, the threat from quantum computers. And here's the really scary part. Most of the asymmetric algorithms we use today, the safes in our system, could probably be cracked pretty easily by a powerful quantum computer. So what are adversaries doing? They're recording our encrypted data today with the plan to harvest now and just decrypt it all later once they have a quantum computer up and running. This means we have to act right now to protect today's secrets from tomorrow's threats.
And this is where the true genius of the hybrid design really shines. Because we separated the jobs into a KEM and a DEM, a safe and a lock, we don't have to throw the entire system out and start from scratch. The model itself is incredibly flexible.
We can basically perform a kind of security surgery. It turns out that symmetric algorithms like AES are actually thought to be pretty resistant to quantum attacks. So we can keep our fast and reliable DM, the lock. All we need to do is replace the vulnerable part, the KEM, our safe, with a new quantum-resistant algorithm. This lets us transition to a quantum-safe future smoothly, without having to rebuild everything from the ground up.
Okay, let's bring this all home. Let's answer that original question once and for all. Why do we go through all this trouble? Hybrid encryption is not just some extra layer of protection. It's the fundamental design, the core architecture that makes modern digital security practical at all. It very cleverly combines the raw speed of symmetric encryption for all the heavy lifting with the brilliant security of asymmetric encryption for the delicate key exchange. Without this elegant balance, the fast, secure, and scalable internet that we all rely on, it just couldn't exist. It really is the unseen engine driving it all.